Okay, welcome back everyone to our series of lectures on the double operatic theory of systems. We are still on Moore machines, and today we're going to compose some more Moore machines. So the thing to remember is that we had this sort of situation. We had some sort of category, like we had some notion of bundle. So this was going to be our category. And so it's going to be a category E over B, and I'll call this P, where E is going to be our category of bundles. B was going to be our category of spaces. And P was going to be a vibration. And this means that we can pull back bundles along maps of spaces. So let's see some of our examples here. E, P, P. We saw before set, semi-direct product set over set. This is what's known as the simple vibration of set. And just to remember, we might think of these as being like trivial bundles. So this was pairs. These were product projections. And this was the base of the product projection. And this sends that product projection down there. So we might think of these as trivial bundles. In the sense of differential geometry, they have the same fiber or the same top part in here for any element of the bottom part. Okay. And then we also saw vector bundles. Over manifolds. And again, it looks very similar. But now, in this latter case, right, the bundles don't need to be trivial necessarily. And then, in addition to that, we also had some other data. I'm going to give myself a little more space here. We also had some other data that was important to describe the notion of system in this setting. We also have a section T, so that PT is equal to id B. That's what it means to be a section. And this here is going to be the bundle of changes. Something like a tangent bundle. So in this case over here, it really was the tangent bundle, T. And in this case over here, it's something that's a little more trivial. We send A plus to A plus times A plus. So it's what you might call the diagonal. And the idea of the bundle of changes is that you have over M, you have Tm, and if you look at a point in M, and you look at the fiber over that point in Tm, then this are the changes possible in state P. So in the theory of ODEs, the changes possible in the state P are precisely the tangent vectors to P. So you make an infinitesimal change, and you say how you're changing. But in the discrete case, we have a Moore machine. In the discrete case, a change will be what is the next state. Now note that if you wanted to, you could actually put a functor in this second component here, which we talked about earlier, and get other kinds of if you wanted. So let's talk about how do we get Moore machines. As we mentioned last time, given this setup, right, we have two kinds of maps in E. So when P is a fibration, and I should probably remind us what a fibration is. So a fibration means that if I have some kind of bundle, E, different font, over B, and this is what I will write this to say that E here is in E, B here is in B, and PE equals B. So I'm writing that maps to symbol to mean that. And I have any B prime down here and some function F. Then what it means for this to be a fibration is that I get a bundle F upper star of E over here, over B prime, and a map here, which is called the lift of F. And I'll denote this with a little brackets here, and then give myself a bit more space. And this has a universal property. So I'll write, I'll say, I'll now do my universal property. Maybe I can get a slightly better color here. Yeah. So for all, oh, wow, that's giant for some reason. Why is that so giant? For all in the green, so I'm going to take a whole nother thing up here. So I'm going to take some other, wow, why is it so thick? Is this okay? X, yeah, fine. X over Y. So those are too fancy. X over Y. Maps down here. So for any other bundle like this, which I'm thinking of, I'm writing this maps to because we don't, a priori know that everything in E is actually functions in some other kind of category. But in general, this looks like a bundle. These diagrams look like the correct diagrams when they are actually maps, And for any map of bundles into here, which is X into E, and for any commuting square on the bottom, right? So I will write this as B prime, and this is FB prime, and this here is E. Then there exists, so it's for any in the green, there exists a unique in the red, there exists a unique map of bundles like this, where every map of bundles maps down to the thing below it in the diagram. And if you've seen the universal property of the pullback before, you can recognize this as a form of the pullback universal property. Okay, so that's what it means to be a fibration. And so there are two kinds of maps in, so I'll say that anything up there, anything here, so we always say that it's a fibration when I should maybe note, there exists an F, there exists a F, there exists this dashed lift such that for all there exists. It's a for all exists, for all there exists unique. It's a classic category style statement. So if I did everything in different colors, which I wonder if I can do. Thank you. Said, I don't understand why it makes it so huge. Okay, change style. Oh, I see. Yeah, something like that. Okay. Yeah, so then and then I can only have three colors loaded, ready to go, huh? Really? Okay.
You click the pencil itself instead of the colors.
That down here? Oh, okay, thank you. Although they're different colors. For all, there exists, for all exists unique. I like coloring my category theory diagrams like this so you know how to read them because it's actually kind of complicated. It's almost like we're doing analysis with this many quantifiers alternating. But so that's how to read this diagram. So that's what it means to be a fibration. For any dark blue, there's this light blue, such that for any green, there is a unique red. Okay. So that's what it means to be a fibration. And so so this implies that E has a factorization system, which is called vertical Cartesian. And the way that works is a vertical map is a map of bundles, which is over an identity. And the Cartesian one is a map of bundles which has this universal property on the right. So it's something of the form F upper star lift F. It has the universal property as on the left, excuse me. And the reason every one factors like that is if I draw a generic I have this generic one. Well, I can put again down here the same, and this is F, and this is like say F over bar, which is something else. I can put here F again, right? And here I can put this equation here, and then I get F upper star E prime, which lives like this, and this is pullback, or it is Cartesian. And so by the universal property, I get a unique like this. And you see I've taken the original morphism F bar and I've factored it as something vertical followed by something Cartesian. But then, moreover, we also have lemma pullbacks of vertical along Cartesian exist and are vertical or Cartesian respectively vertical Cartesian. So I'll say what that means. Suppose we have maps. So it's gonna be a cube. So I'm gonna do my best. So E1 to E3, E2, E3, and this maps down to B1, this maps down to B2, 3, this maps down to B2, here. But now I'm going to say this one is going to be Cartesian, and this other one is going to be vertical. So let me actually write that out. So if this one's vertical, right? This is an argument that's going to feel familiar from last episode. If this one's vertical, that actually means that this bottom thing is not just E3, it's actually E2. They're the same. And now I want to sort of quote unquote complete the square. And now I see the problem of doing it quite uniformly like this. I should have made one side a little shorter. Okay. And then I'll put this one over here. So now I want something down over here. That satisfies a certain universal property. So again, I want this pullback to be of the vertical to be vertical, and I want the pullback, this one's Cartesian. I want this back square to be Cartesian. So that fixes a lot of things. Because I want the pullback of the vertical to be vertical, I'm forced to take this back thing to be B1. And now the question is, what should I take to be that top item sitting over B1? Well, I have up here this map from I am also forced by the fact that I want the back to be Cartesian. So if I call this F and this F bar and this G bar, this is the same argument we did last time. Then this is going to really have to be this is also F. This is really going to have to be F star of E2. And then I have to go from F star of E2 to E1 somehow over B1, but I already have a G bar into E3. Sorry, let's do this right. So I need to go, I'm seeking this last thing here. So I'll put that up here. And what I have, and essentially haven't used yet, is E2 to E3. So I can pull this back along F to get F star G bar from F star E2 to F star E3, right? But now we can note that actually, this one here, I forgot to fully clean out this diagram at the beginning. We assume that this front square here, I'll highlight, this one here was Cartesian, which means that E1 was actually already F star E3. And so we can correctly make this top one F star G bar. And if you remember our construction last time with doing this, constructing lenses in this way, or filling out these squares last time, in the case of the simple vibration, you'll recognize that the argument has the exact same form, but it's a little more abstracted now. And then you do have to check that this has the correct universal property. So let's see how that goes. So if I put a thing in here, I'll call it x naught and x1. I need a unique thing here, right? Now note that in order to give a map into F upper star E2 from X, it'll suffice to give it, I'm not going to draw the bottom of X because it will make it too cluttered. It will suffice to give a map into E2 that sort of makes that bottom commute if it were there. So we better be able to get that from the other one. And indeed, we do have it on the other one because maybe I should draw the bottom. So sorry, I'll move it slightly over. Three-dimensional diagram here. X, E, like this. And then X down. I'm going to put it way out of here. X down to Y. And then whoa, like that. Whoa, like that. And we have these squares here. That's what maps do. And this Y goes all the way down there. Maybe I should be doing these in a different color. So this here, This goes all the way into here. This goes all the way into here. So that's what I start with. And now I need a map into here. Now that bottom one's very easy because I actually already have a map into B1. It's the one that's over here. This one equals this one. The fact that the bottom outer square commuted tells me that this little triangle here commutes because it's this, then F equals that whole thing. And that's exactly what this says. This, then F equals that whole thing. So that's the same. Now up top, look at this. I have one of these with a full triangle on the bottom. There exists a unique one here for that. That's just the property of Cartesianness. So that's what makes this a pullback. So as a corollary, so I'll say this, is that so we can turn this into a corollary. If P, E to B is a fibration, then E vert cart is what is known as an adequate triple. And an adequate triple here is just something that you can take spans in, but it will be, so an adequate triple definition consists of C, L, R is a category C with two classes of maps. L and R. So that one, L and R contain all identities and are closed under composition. Two, if I will do a nice little for all exists diagram here. For any diagram like this, where this one is in L and this one is in R, there is a pullback. Where this one is in R and this one is in L. And I wrote those labels wrong, so I'm going to do that. It doesn't make a difference, but it sort of does. I just can't remember my lefts from my rights. This one points left, so it's an L. This one points right, so it's an R. It doesn't really matter, but okay, here we go. And furthermore, you might also say that another thing to say is that, and if we have a pullback in L, in R, so this is any pullback whatsoever, not just the one that we asked that it would exist, and I call these two P1 and P2, then P1 is in R. Oh, I did it again. The most difficult part of category theory is keeping your left and your right. P1's an L and P2 is an R. Okay. So that's just saying that it's not just that there is such a pullback that has this property on the legs. It's any pullback has this property on legs, and there is one. So, okay, that's just a way of saying that. So to say this corollary is just a way of saying, well, we check that for when you have a fibration, the top of the fibration, which is the category of bundles itself, has this structure. We didn't check that verticals and Cartesians were closed under composition. I leave that up to as an exercise. So, okay. So then we're ready to define a lens. So definition, and this was originally due, or an equivalent version of this was originally due to David Spivak. If E to B is a vibration, a P lens, or we'll usually call it an E lens for short, but it really does depend on all the P, is a span in E with left leg vertical and right leg Cartesian. So this is something of the form E naught, left leg. This is vertical. So so I guess I'm going to write it in my plus and minus form now. A minus, A plus, and this is here is A plus, B plus. So such a thing consists of two maps, which I'm slowly in the process of writing. B minus here. This is F. This is going to be F sharp. It's going to be F upper star B minus. Just in here, S. There we go. So that's a lens. As you can see, we could write this again as F sharp from A plus, A minus, left to right, B plus, B minus, because it only has these two bits of data. The rest of the top of this one for here is determined by this thing is that must be the lift of this thing because we asked it to be. We asked that right hand side to be Cartesian, and we said this hand side was vertical. That means this must be the identity. And so now we can consider what composition of these things is, and composition is going to be given by composition of spans, which I'll do out here. Why so high? So here is G sharp. Here, over here, this is F. So what is that composite of spans up here? Well, we already know that at the bottom, it's going to have to be A plus. So I'll put A plus up here. And it has to be the equals up here. And down here is going to be F. This one's called G. And then above it, here, we already know what that has to be as well, because it has to be F upper star of G upper star of C minus up here, and this here is F upper star of G sharp. And that whole square is a fullback here in this. In other words, the rule for the composition actually gets a little simpler magically at the end of it when we look at it this way. Why? B minus, C plus, C minus. This is F sharp. This is G sharp. And that is equal to A minus, A plus, C minus, C plus, C minus. G after F, and F sharp after F star, F upper star, G sharp. Which is a nice, gives us a nice little notation that cleans up something we saw a number of times ago. And it's worth working out exactly how this works in the simple vibration straightforwardly to understand. Maybe this is a time to note that on my website, which I suppose will be linked in the description, I have a manuscript where much of this is written out in great detail, so you can follow along. Although some of the concepts are not in the manuscript, they're a bit new. Like this adequate triple formalism as a way of understanding this is not quite there, but you'll recognize these formulas.
No, sorry,
Yeah.
maybe it's a very subtle point, but the third condition for adequate triples was that any pullback of an R along an L is another R and an L. Is that right, that one there?
Yeah.
Is that strictly true for vertical maps of vibrations, or does it need to be ellipsoidal, like?
I think you're right. It needs to be like vertical. There's a few things that would need to be totally to get this to work sort of very correctly. You really want L and R to contain all isomorphisms and be replete under isomorphism. And you really want to take vertical, you don't even actually have a factorization system, vertical Cartesian as I described. At least it's not orthogonal. I mean, it's not unique. For it to be unique, you need to define vertical to be something that maps over an isomorphism. So that is correct. Yeah, I'm sort of, as you can see, I'm sort of implicitly invoking the Grothendieck construction here to bounce back into something that's, when you do it in the indexed way, you can avoid those and strictify the whole situation. But then you also have to, in order to prove this, like technically, if you do it in the index category point of view, you actually get an extra little thing in here, which corresponds to the fact that it has to be a G after F star.
Right.
For the domain, for the correct domains dilemma, if you do it in the Grothendieck construction. So yeah, you have to smuggle in your coherences somewhere. Okay. Right. So the point of doing this again was to describe the general algebra for wiring together dynamical systems. So the one thing I wanted to go back to is we're going to say that in general we can now describe. So given E to B called P and a section of it like this, we define a TP Moore machine to be a lens of the form TSS, and then we have here is E to O to I, E star I, U, like this. And that's our general notion of dynamical system in this so-called doctrine of dynamical systems. So we'll see plenty of other kinds of dynamical systems, like labeled transition systems don't really fit into this mold. Various other kinds of things, various things represented by graphs, circuit diagrams, all that stuff don't really fit into this mold. But systems of ODEs do, Markov decision processes do, various kinds of automata do. So this is, as we discussed last time, this is a parametrized dynamical system. Parameterized system of ODEs. This thing here, this thing is called the interface. And again, we see that systems can be acted on the right by lenses, by composing. Because again, composing doesn't change what the left-hand side looks like, and all it takes to make this a system is that the left-hand side has that TS. Okay, so let's actually describe how we can get, so this is a very general definition. It specializes to all the cases we've discussed so far. We'll come to sort of functoriality theorems we can define. So compositionality theorems we can prove that let us change the flavor of more machines. So we can, for example, we'll look at a morphism that takes a continuous system and discretely approximates it. We'll see that as a sort of map of these kinds of things, these vibrations with a section. I call these things, by the way, tangencies. So we have a Moore machine. For any notion of tangency, we get a definition of Moore machine, and eventually we'll get a whole, like a sort of algebraic structure of Moore machines composing, which will be our algebra for double operads that name sort of the double operatic in the systems theory. Okay, let's step back from the abstraction and go back into something quite concrete. So more wiring diagrams. So remember, if you will, that we had procedures, we had some kind of, implicitly, we had some kind of procedure for taking diagrams of this form and turning them into lenses. Right? So first of all, we imagined that our diagrams were actually labeled with a bunch of things like sets here. And then we went and read off what this actually must mean as a lens. So the interface of this is the outers. So the interface goes from inner to outer. And the interface of the outer in this example has an output E and an input A times B. And we're back in the simple vibration. So now we're in, say, simple vibration. And over here, we take all the inner outputs, and the inner outputs are C, D, E. Well, I'll write it as two separate things. It's actually worth doing that. So the first box here is C times D, and its inputs are A times C. And we pair that up with, excuse me, I used a parallel last time. We pair that up with the inner inputs for the second box, which is D times B and E. And we have the lens here. And this lens, W sharp, corresponds to this wiring diagram. And what is it? Well, we sort of just read it off. So W of C, D, E is going to be just E because we just project out that E. As you can see from the diagram. And the W sharp also we just read off, but we have to remember the entire signature is going to take in an A and a C and a D and a B, or excuse me, that's wrong. It's going to take in a C and a D and an E, and it's going to give out a and a and a B. And then we look at the picture and we're like, well, okay, if we start with a C, D, and E, and an A and a B, then how do we fill in all of the inner inputs? Well, we take the C and we feed it into the C position. We take the D and we feed it into this D position. We take the B and we feed it into this position. We take the A and we feed it into this position, and that's it. We don't have to do anything with that E. Doesn't go to an input. So we just write that out. Over here in the back, it would be A times C times D times B. That's the order we wrote it up above, just to remind ourselves. So parenthesize like this. And we just see that the A is in fact the same A, the C is in fact the same C, the D is in fact the same D, and the B is in fact the same B. So the point to understand here is that this really doesn't seem like it's doing very much. So now I would like to give a story where we can see the diagram itself, which is some kind of combinatorial picture object, as this lens, or at least as a lens directly. Okay. So how do we see the diagram as a lens? So the diagram as a lens, we might note that in general, these don't all have to be distinct sets. They could be, some of them could be the same. So this E could in fact also be an A, right? Just to note, this could also be an A. I just replace it up here, the A. Everything works the same. They don't actually have to be distinct. But if I can't have this middle one be both a D and something different, right? I can't be a D for this wire and something else for this wire. If the wires are connected, they have to be the same. So we'll start by taking a labeling graph here, and we'll say that it's labeled, well, not exactly in sets, but in just some general kind of label for what kind of thing is allowed to flow there. Right? So we'll suppose we have a set L of labels. And let's look at what the actual combinatorics of such a diagram is. So let's define a box. So a box is a pair of finite sets labeled in L. By this, I mean a set X together with a labeling function to L. So, right. And it's a finite set. So what do I mean there? Well, it's going to be, I'm going to write it as, we could call it B out, B in. And I'm going to suppress the labeling, but really we all have labeling functions for both B out and B in. And so what does that mean? Well, I'll write that as if I have a box, right, it has actually some set of inputs and some set of outputs, and each of them, so I'll name them all, B1, B2, B3, B4, B5, B6, B7, and they all are labeled by something, but I'm going to suppress the labels. Everything here just requires that the labels match up. Well, so here we have B in is equal to the set B1, B2, B3. B out is equal to the set B4, B5, B6, B7. And that's how we say this box has three inputs, and these specific three inputs with these names, if you will, and these outputs. And they each can label, they might have the same label. And that label will come up later when we ask what type of data is allowed to flow on these wires. So another way to think of these labels as being types. So we're going to ask what type of data can flow on these wires, and this we'll think of as variable names. So a way to write the labeling function would be something like X, which is in our set X of variables, has type, the label of X. It's one way to think of it. And you can see that every variable has a unique type, but multiple variables can have the same type. So as a note here, if I have one of these, X doesn't really come with an ordering, but if I were to order it, I could write such a thing as X1 of type L1, X2 of type L2, dot dot dot, Xn of type Ln, where X is equal to X1 dot 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 Xn, and L from X to L is defined by X Lxi is equal to Li. So I can define it, this is a single object, and this here we'll call a context. That's what it would be called in type theory, context. So a box is really a pair of contexts. By this rearrangement, it means the same thing. It's a finite set labeled. We could think of that finite set as the names of the wires, and the labels as like just the thing that's going to help us make sure that we always plug the right wire into the right other kind of wire, so that when we interpret it, we don't end up with garbage in, garbage out kind of thing. But we can also interpret those finite sets as variable names and those labels as their types, which is how we want to think about it ultimately when we do systems, because we think about the variable name as naming whatever is being carried along that wire. So it names an element of the set that's going to be carried along that wire. So a box is a pair of contexts. And then we can ask, what is a wiring diagram? So a wiring diagram. Well, let's see what it would take to define a wiring diagram. I haven't actually set the rules of the wiring diagrams, but we'll say this, right? So the rules are, so one, every so it has a wiring diagram has some inner boxes. Some inner boxes, and then I'll write it in the lens notation to some outer box here, which I'll call some. There's no reason to use this, but I'll use X out, X in. So this is the outer box, and these are the inner boxes. And then we're going to give the rules for wiring, and the rules for wiring are going to be that every inner output is connected with a unique outer output, excuse me. And every inner, sorry, I believe it's the other way around, excuse me. Outer. Every outer output, that's a unique inner output. So if you, this is a way to ensure that if you're looking at the outside of this composite, you'll get something from the inside. If it were connected to multiple things in the inside, you wouldn't have a uniquely determined value to read out. You would have to say add them or superpose them or something else. So before we'll get to diagrams that allow you to actually functionally act on these boxes soon, but for now, we just want to be able to read some output out of our box directly, and that means that every outer output has to be connected up to some unique inner output. And then we also have that every inner input is connected to either an inner, I'm sorry, an inner output or an outer input. Okay. So, so if you look up above, you see that these rules are satisfied, right? Every inner input, so something like here, comes from either, in here, it comes from either an inner output, which would be one of these, or an outer input, but that's what actually happens for this one. But if I look in here, it's connected to an inner output. And you don't have both, because if you had both, like if this was connected both to this and to this, you see you would have to at some point combine the signals. And we will allow combinations of signals, but you're going to have to specify exactly how you want to combine them. So we'll do that later. Once we understand the sort of deep reason why these wiring diagrams are the way they are and how they relate to lenses, we'll be able to quickly generalize our notion of wiring diagram to all sorts of other cases. Okay. So how do we formalize this notion? Well, it's clear that we can sort of turn these into two functions. We can turn it one into a function w that goes from x out to b1 out plus dot 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 plus bn out. And then we can also have this w sharp here that goes from, so in other words, every outer output is connected to, this is a disjoint union, is connected to one of these inner outputs. And every inner input so it's for all I, but I can bunch that up into a single function, is connected to either an inner output, excuse me, or an outer input. So if you look at this, it's exactly the backwards version of what a lens is. That's the combinatorial story. But if we remember that these are supposed to be variables, we get an actual very interesting thing here. Because one thing we'll be able to say is, remember that these were lists of variables. And so what we are saying is that the data here is telling us how we are going to substitute some variables for other variables. So, in other words, in here, we say that for any, we have, excuse me. So this is a, but I'll just say this is a lens in fin over L op. So where we used to have times, we now have plus, because that's what times is in the opposite category. And where we used to have maps going one way, we now have maps going the other way because we took the opposite category. So that's the main observation here. But we can make a further observation, which I think I'm sort of pussyfooting around here, which is the theorem, is that fin set labeled in L op is the free Cartesian category that is has finite products generated by L. So what that means is that functors from fin over L op to any C that preserve products are the same thing as functions into objects on C. Or it's perhaps better to just put it as functors from the set L into C. Excuse me. In other words, if we give a bunch of objects in C for every L, then we can interpret any set labeled in it that way. So let me show you how that works. And then we'll come back to this context notion, why this is a very nice way of thinking about this. So if given, maybe I'll call it, instead of this, I'll do C equals this. Given C from L to fancy C, i.e. for all L in L, for any label, we have an object CL in C. And then we're going to define FC. And prove that it's product preserving. So how do we define FC? Well, if I have a function from X to L, right, which is my labeling, then remember that C has finite products here in this thing. So I can take the product in C over all X in X of C L of X. And that's a well-formed formula. And then I need to check that this actually gives me a functor. It's like not super obvious from this definition that it gives me a functor. And this is where we see the contravariance come in. So if I have now a map that I'll write it backwards. This is a map from X to Y. And they're both over L. This is the labeling of X and the labeling of Y. Right? And this commutes. Then f of this has to be a function from the product of X and X of CLX to the product over Y and Y of CLY. Right? By construction, right? And I'll call this thing here little f. By construction, by the universal property of the product, it suffices to give all the other maps. I could say it, or maybe I'll note something. We'll note that this commutativity says that the label of f of x is equal to the label of x. That's a fairly important thing to note.
Label of f of y is label of y?
Yes, thank you. That's right. The label of f of y is the label y. Right? So in other words, if I have from here, so in other words, we also have that C of L of f of y is equal to C of L of y, because the labels are the same. And so, pause it for a second. Yep. Hey, so thank you, Jason, for telling me how to do this. So to define this map, we need to define for any y in y, we need some map from the product of x and x of CLX to CLY. That's by the universal property. And what we can do here, right, is we note that we have this is equal to CL of f of y, as we have said over on the other side. So we can take the projection on to f of y. And it is perhaps not terribly obvious that this gives a functor, but it does. And it is perhaps a bit more obvious that it preserves products because we've sent it to the product over all the elements of X and X. And if we take the disjoint union of two of those, we'll end up with the product over just more things, so more products. Okay. So this relates to this idea that if it's a free Cartesian category generated by L, it has its own little internal type theory. So the internal language. So N or L is free Cartesian category on L generators. So it's also, this means it is essentially the free type theory, free simple type theory with basic types L and L. So let me explain how that works, right? In other words, as we've seen already, an object X2L can be interpreted as a context X1 of type L1, comma, dot, 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 Xn of type Ln, where we have that X, where L of Xi is Li. Now, a map from F to Y, L, can be interpreted as a substitution from X1 of type L1, dot, 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 Xn of type Ln, to Y1 of type L prime 1, dot, dot, Ym type L prime n. So what does a substitution like this mean? Well, a substitution like this is going to be a way we have to write down. So for all I equals 1 dot 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 m, we need to write down an expression x1 of type L1 dot 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 xn of type Ln yields some question mark of type L prime I. That is, we need to give something that we can take yi is equal to some expression of the x1 dot 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 xn. To say that this is a free type theory means we're not allowed to do anything but just have that variable be one of the variables we already have. Right? So this must be x of f of I. And in order for this to be well typed, we must have that L prime I is equal to Li, or L of f of I. And that's how we end up with interpreting this as just a bunch of the function on the left gets interpreted as an expression that is well typed in the context of x for all the y's. But because we're not allowed to do anything with this, because we haven't added any other kinds of operations, right? Excuse me. Because we haven't added any other kinds of operations, there's nothing we can do except use one of our variables. So it's a type theory where we're just keeping track of what types all our variables are, and we don't have anything else going on. And if you package all these up, you get a single big package here, which is the X bar yields X F Y1, comma, X bar yields X F Y2, and so on. And that's all the different variables. For each Y, we had to pick some element that was of the correct type. I avoided the types, but I have to put them in. And this is in type L, Y1, and so on. And in order for that to make sense, we need that has to be equal to F of X, I, of X, F of Y1.